Please go ahead.
Mike, do you have it? Okay, thanks. How's it sound? Good. Yeah, so I'll pick up where John left off and talk about using polyatomic molecules for precision measurements. In particular, mostly on the SRH experiment, and then at the end, I want to start thinking about using nonlinear molecules, which have certain advantages for future measurements with higher sensitivity. So this is going to be all the cosmology in this talk. There is dark matter. Dark matter seems to be some particle. It has some mass. We don't know what the mass is. And depending on what the mass is, there are different kinds of fundamental physics models that might account for the behavior of dark matter. And then where our lab experiments come in, and in particular our tabletop AMO experiments, is we start thinking about if the dark matter particle has some mass, what kind of experiment can we do to detect it? And the experiment for measuring dark matter models that I'll talk about is particularly looking at this ultralight dark matter range between about 10 to the minus 22 eV and 1 eV. And if dark matter is in this range, it would have a large Compton wavelength. We know from astrophysical constraints that it's cold, and it would behave essentially like a BEC. And that results in an oscillating background field of this field, right? For us, say this should be a scalar particle in models we're considering. And so this oscillating background field could couple to ordinary particles, and that would modulate the properties of ordinary familiar standard model particles like the electron or the proton. And that coupling, due to the oscillating amplitude of the background field, would result in an apparent oscillation of things like the masses of the ordinary particles we are used to measuring properties of. So we're looking at using SRH in particular, and I'll explain a little bit why. So if the proton or electron mass is oscillating in time, the ratio between those will likely oscillate in time. The coupling to these particles is very unlikely to cancel each other out for this ratio. And because molecules have energy levels that just generically depend on the proton-to-electron mass ratio, for example, rotations and vibrations, these energies will oscillate in time. And if you find two states that have a different dependence on the proton-to-electron mass ratio, then a transition between two energy levels will also oscillate in time. So here we show an SRH molecule in a bending vibrational mode and in a stretching vibrational mode. These may be higher excitations than just fundamentals, that's fine. And because the bending vibration is more anharmonic, this has a different sensitivity on this constant mu, which is MP over ME, than the stretching vibration. And the transition between them will show a signature of that oscillation. If you can find two states like this that are very close in energy, then you can get an intrinsic enhancement because the absolute oscillation amplitude of these energy levels is set by their absolute energy. But if you just find two high up energies that happen to be close and have different sensitivity, then they have this absolute amplitude that's set by their energy relative to zero, but the relative energy may change a lot. So we think SRH has transitions up to enhancement of the relative sensitivity by about a factor of 10 to the 3. What that means is if we want to measure a mu variation to part in 10 to the minus 17, we only have to measure the transition energy between these states to about part in 10 to the minus 14. So this is good for two reasons. One is the fractional precision is easier to achieve experimentally. And the other is it moves these energy scales from about 10 terahertz, typical for these vibrational energies, down to maybe 1 or 10 gigahertz, which is much, much more convenient experimentally. So the experimental steps to actually get there, we first produce SRH molecules by avoiding a starting metal target. We flow in water vapor and also helium, which is cooled to about 2 Kelvin by the walls of the cryogenic buffer gas source. Then we slow the molecules by counterpropagating lasers against them. And after many, many photon kicks, these molecules will slow down to a velocity where we can capture them in a MOT and cool them and trap them. Then we can do all the tricks that John just described, sub-Doppler pool, transfer to an ODT with high efficiency, we think, now with all the tools that have been developed recently. And for the most convenient precision measurement, you don't really want to do it in a Mott chamber. You want to transfer it to some dedicated science chamber where you can very efficiently shield out magnetic fields and control electric fields. So yeah, then we will do precision spectroscopy. So we can do this mu variation measurement I talked about, or an EDM measurement that I'll talk about at the very end with a bit of a twist on even further improvements specifically for the EDM. Although SROH is actually an excellent species for the mu variation already, it doesn't help to go to more complicated molecules. What we've done now in the last couple of years is this stuff above the red line. We've produced high flux slow beams of SROH molecules. We've slowed them and we've actually trapped them in a magneto-optical trap. Then we're now moving on to improving the capture and the slowing, transfer to an ODT, and all the other steps. The first step in really convincing yourself you can do this experiment is think through the optical cycle, because that slowing step in particular, and then also the magneto-optical trapping step, requires scattering around 10 to 20,000 photons. And if you drive an excitation from this ground electronic level to the first excited electronic level, you'll get vibrational decays to many different states. So the character of each of these states is indicated with these cartoons. We have bending modes, stretching modes. Some of them are combination of bend and stretch. Some have higher than fundamentals. And in order to do this design, it helps to measure all the branching ratios directly. So this is a spectrum we took a couple of years ago where we drive this excitation and then we can disperse the fluorescence on a spectrometer and count the amplitude of decay at different wavelengths, which tells us how much population goes to all these various states. Once you know that for all of the really highly addressed excited states you're going to use, you can start laying down all these arrows and figure out something that makes sense. I will give a caveat that actually our original design has changed a little bit, because once you start doing the experiment, you start realizing some details that might modify it. But this is a really essential step. And I think measuring these branching ratios is the first part along the path to working with the new molecule now. Some of these states required spectroscopy to find them, either find the vibronic level overall or just find the rotational level we're going to use. So I want to give an example of one of the states we found. We started with pulse excitation using the spectrometer that I just alluded to. So here we're scanning a pulse excitation laser and we disperse the fluorescence. So each of these vertical slices shows the different wavelengths that are emitted when we excite at one energy. And as you scan the excitation laser, you can get bursts of fluorescence in very narrow regions. And by looking at the patterns of the decays and also what is a reasonable excitation energy, you can figure out what the identity of these clusters of fluorescence are. And then you can support the assignment by going and doing CW laser excitation somewhere around this and start seeing lines and look at rotational spacings. And if those are all right, then you must have the right state. In this example, it's actually very nice that SRH had been very thoroughly studied. So this is not a normal journal molecular spectroscopy kind of spectrum. Usually you have kind of a dense line of data points. But once we found something, we can just jump a known spacing and confirm it, and jump another one, confirm it again. And we can save actually a lot of time because this molecule is really well understood already. If you find a new state, it's also nice to go and check the branching so that you know if you send a ground state or some new excited state you weren't using before, you're not going to get a lot of decays to something that will slow your optical cycle. So we did this for a number of repumping transitions. And then we can build the optical system. Unfortunately, this actually spans around 100 nanometers in wavelengths, but unlike the CAF experiment where that covers a very nice, pretty range, these are all just red. But that's what we have to live with in order to use strontium. It looks like this might be really daunting, and it was, of course, a lot of work. But I want to advertise, John already alluded to this, that these SFG systems are very, very robust, and they just work every day once they're set up. So it's very reasonable to scale these systems up to many, many lasers. We could go well past 10 and I think not have a problem with running the experiment reliably every day. And actually the home built SFGs, where we take high power fiber amplifiers, combine them, overlap, send them through an SFG crystal and get some visible light out. Those I'd say are our most robust systems, more than any commercial laser we can buy. Another nice thing about these home built systems is you can buy a couple of fiber amplifiers, which are really the expensive part of the system, and then seed one amplifier with multiple wavelengths. The amplifier will amplify both of those up to the total power being the max the amplifier can generate. And then you can send that through one crystal, which is tuned to use one of the seed wavelengths to give you the visible light you want. And then send the rest of the IO light into another crystal, which is tuned to use the other seed wavelength and get different visible light you want. This actually saves the total experimental complexity and cost quite a bit. You can also share powers from one amplifier. And by playing tricks like this, actually the whole system is pretty reasonable to build. So then once we have all these lasers, we overlap them. We have 10 slowing lasers as well as one laser we send in to increase the molecular production by driving an atomic line. And we send them counterpropagating the laser beam. This is a photo of our apparatus. So the slowing light comes down here, goes through our cryogenic cell. The molecular beam is going to the right, and then it's a little hard to see because the experiment is large, you can't really see everything. But the mod is down in this chamber here. So it takes about 20,000 photon kicks to stop the molecules. Our photon budget is a jargon we use to represent the average number of photon scatters before an unaddressed vibrational state is populated. That's around 13,000 photons. So we take some statistical hit, about maybe 80% of the molecules are lost to dark states before they get stopped in the Mott chamber. Initially, we used something called white light slowing, where every single laser frequency was spectrum, had a broadened spectrum, and that allows each laser to address the full span of substructure from spin rotation splittings, as well as Doppler shifts, to stay resonant all the way along the slowing path. Now we've switched to frequency chirping, the first repump, which gives us a factor of a few improved Mott loading. And in that scheme, the first repump is resonant with just one velocity class, which we start at high velocity and then we sweep it down to target resonance with stopped molecules when we want them to go into the Mott. So we check, can we do slowing? This is supposed to be, from lore in the community, the hard part of the experiment, making sure the slowing works, because that really checks your optical cycles okay, and all your lasers are basically doing what you want them to do. So you start with an unperturbed molecular beam, which is peak at some high velocity, probably 110, 120 in these data. And then if you turn the slowing lasers on, like this cartoon up here, then you lose a lot of molecules from decay to dark states, or you turn them around, or so forth. But you get some molecules down within the Mott capture velocity range, whereas before there were none. This is another way of looking at the same data, where you can look at the arrival time of molecules. If you don't slow, all the molecules showing up are very fast. If you do slow, you get some arriving over some range of times, which are around 40, 50 meters per second in these data. The difference is really, I think, is convincing, where you're taking population out of the high velocity and putting them into low velocity. So this is great slowing data. We were happy with this. Then we moved on to the Mott, and skipping 9 months of very painful work, the Mott worked. This is a picture of our Mott. This has about 2,000 trapped molecules in it. We can generate this about once per second. It's our rep rate. And the lifetime of the Mott is currently limited by decay to vibrational dark states, just because we can scatter only about 13,000 photons, and you need some scattering rate in order to keep the Mott alive. And you can see that here at very high powers, you run through that photon budget quickly and the lifetime is short. At lower powers, you run through it slowly and the lifetime can get pretty long. If you try to go much lower power than this, you just can't hold the Mott anymore and they'll fly away. Another way to look at the photon budget limit to the lifetime is we can just turn off some of the late repumpers after we've loaded the Mott and then see how the lifetime changes after that. So our full photon budget is around 13,000 photons per molecule, and that's where we get this long lifetime. if we start cutting out wave repumpers, we can decrease that photon budget, and the lifetime just scales linearly as we would expect. Then we can just characterize the MOT in the usual way. We can measure the size versus the MOT beam power or the temperature. We get about 1 millimeter MOT size or about 1 millikelvin. We can displace the molecules by pushing on them with the main slowing laser, which exerts a large force. Normally that's off during actually holding the MOT, and then turn that off, and they'll ring down, and this works at all sorts of different capture parameters. And really all this slide is telling you is the MOT behaves completely as expected. This is just in some sense a boring MOT, except it's exciting us because it's SROH. There's a PSA I want to give, which is that we tried a long time to get a really good, reliable MOT with 1 centimeter diameter laser beams in the MOT region, and it was pretty spotty. It depended a lot on our beam parameters, and the signal was not that great. Then we increased the beam diameters to 2 centimeters, and it just worked fantastic after that. We think this is just a result of the high mass of the molecule, which leads to low accelerations per photon kick, and the low scattering rates, which you somewhat inevitably incur by having many repumped states, because you spend a lot of time in various ground states which aren't contributing to your forces. And this combination means the capturing forces are not very high, or the accelerations specifically are not that high, and it helps to just have a larger capture volume. So now we're further improving the optical cycling. We're doing spectroscopy to find what we know our next repumpers are. These are based on the dispersed fluorescence data I mentioned before. We already found one of these next repumpers pretty quickly. We're working on finding the second next repumper. We'll add those in and get more photon budget. One interesting thing that may be an issue for more complicated molecules as we really push this technology is just in the course of doing various spectroscopy, we found some accidental near resonances which can deplete our MOT. So this is our MOT signal as we're scanning a repump, and the repump should make our MOT better, but then you hit some other state and the MOT gets worse. So by looking at spacings between these, we can start guessing what kind of state this is. But as the density of states goes up, these will become more and more likely, and for really complicated molecules, just with a lot of repumps, you might be accidentally driving lots of lines that will damage the MOT performance. So this is something to just sort of be aware of as the density of states goes up and up. It may limit ultimately how crazy the molecules can be and still have this work. So next steps are just get the ODT better, and then do precision spectroscopy. I want to really quickly talk about some more speculative things that we're starting to nail down, which are especially relevant to the electron EDM application that John and Nick have both mentioned. So polyatomic molecules are great because they allow you to orient the molecule in an external field, polarize it at really low fields, and still retain the ability to laser cool and trap the molecule. And there's this idea that in principle, it doesn't really matter what you stick on to the end here, but probably no one in this room believes that, so we wanted to investigate it. And we wanted to approach this from a very general point of view of what is the type of symmetry of the ligand here that still allows you to do the laser cooling. In SROH, we use this vibrationally excited state to give the parity doublet structure, and that limits the lifetime of the science state to just under a second. But if you use an asymmetric top like these two, or a symmetric top like this, the lifetime is effectively infinity. And then the next question is just, can you actually get any of these into the ODT? So we do the same thing we did for SROH. We look at the vibrational decays with a high sensitivity spectrometer when we excite transition. We started with, actually, I don't know what order we did it in time, but I'll start the explanation with SRSH, which is sort of the simplest of these. It's just 3 atoms. It's a bent molecule. And it turns out the decays on this are really bad. There are 7 states that are populated with only 1,000 photon cycles. This is a lot worse than SRSH. And we can actually understand this because all of these vibrational states are the same symmetry. Essentially, it doesn't have enough symmetry in the molecule structure to give any kind of protections against just going wherever it wants. And so you tend to get lots of different vibrational modes populated. A symmetric top molecule is in some sense the simplest. It has a threefold rotational symmetry, but unfortunately has a lot of atoms, this SROCH3 molecule, and that gives a lot of vibrational decays. Some of these are populated. This looks doable, actually, to laser pool. It's probably 12 to 13 vibrational repumps to get into a MOT, which is challenging, but I would say you could do it with tremendous effort. For the most interesting spin isomer, we know from previous work that you have to address two rotational lines, so this sort of becomes 20 to 30 lasers to laser pool in that spin isomer. And so here, many atoms are bad because you get lots of vibrational decays, and the high symmetry doesn't really do anything to protect you from populating lots of these. The most interesting here is SRNH2, which has this twofold rotational symmetry. And it turns out the branching here is actually no worse than SROH. This, I would say, was a surprise to us, even though nominally it should have worked and that should have been clear, but we were just kind of skeptical that you keep adding weirder structures and it still works. But SRNH2 really does not look that hard to laser pool. For rotational closure, I'll breeze through this a little quickly. There's some theoretical analysis that shows for a rigid rotor, there are simple rotational closure schemes you can use for any asymmetric top. In a real molecule, it's a mess. And SRSH in particular decays to several states that are not even microwave remixable. These are very, very far apart because they have to do with rotations of the hydrogens, which have a small moment of inertia. But SRNH2, again, is actually rotationally closed, and you can work through lots of representation theory and build these tables and convince yourself that it's extremely hard for SRNH2 to decay to any rotational state other than what you think is in the cycle. This is roughly speaking because of some correspondence between the symmetry operations and rotations about the molecule axis. The statement is not obvious, I would say, but I suspect this actually only works for things like SRNH2, or if you copy the NH2 on the other side, that would be this D2H group. But this is a very special property. So I just went through this quickly. I'll skip that summary. So I want to acknowledge the SROH team. There's a lot of work that went into all these slides, and this team did it. Alex, in particular, led a lot of the nonlinear molecule spectroscopy, and working in a group with a CAOH MOT and a CAF MOT was essential to getting this off the ground as quickly as possible. So lots of thanks to the rest of the group. Thanks.
We have time for one question. If I can ask, to really gain the sensitivity enhancement, the 203, do you have to drive that condition directly, or you can use Raman or whatever?
Oh,
condition.
We're imagining driving that transition directly with a microwave transition. A Raman transition would also be fine. The only thing you don't want to do is measure the energy of one and then measure the energy of the other. That doesn't give you really good benefit.
Okay. Thanks. One more, yes.
Maybe a rather comment on the same topic. These enhancement factors, they have been very popular already like 15, 20 years ago. They have, as you probably know, be taken with a grain of salt because you cannot measure frequencies of gigahertz to ATAMP injects. So it needs a careful evaluation that you can realize whether the enhancement factor actually focuses on.
Yeah, I would actually, I fully endorse that comment. I would even maybe caution, it's not obvious that an enhancement factor of 1,000 is better than an enhancement factor of 1. That really depends on your experimental precision, systematic errors, and there are actually both approaches of just trying to measure some hard splitting directly versus this approach, and I think this should be pushed on, but both approaches are very interesting.